Hello everyone, today let's take a look at QP number 93, where if I have n chords with uniformly randomly chosen endpoints that are drawn on a circle, what is the expected number of intersections? Basically, if I have a circle like this, we're going to be drawing random chords, n of them, with randomly chosen endpoints. So maybe I have a chord like this. A chord's just basically a line through a circle, so I'm just going to have a ton of basically random chords like this. Maybe I have one that goes from here to here. Maybe this is what it looks like. So I want to calculate the expected number of intersections. In this case right here, I only have one intersection, which is this point right here where these two chords basically overlap. You can see that no other chords overlap in this case. So if I let x be the random variable, that is the number of intersections among these n chords, I'm trying to find the expected value of x. Now we've done so many of these linearity questions, you can see where the indicators are going to come in at this point, right? We are counting the number of something, the number of intersections among these n chords, right? We know an intersection basically occurs when any two chords overlap. Two chords can only overlap at one point, right? We can't have two chords that overlap at multiple points. So basically the number of intersections is just going to be the number of chords that overlap, or the number of pairs of chords which overlap. For instance, in our case, these two overlap. Well, I can define an indicator for every single pair of chords. So if I call this one chord 1 and this one chord 2, I'm going to have an indicator to see if they overlap. In this case, they do. So our indicator would be equal to 1. And then if I call this one chord 3, we'd see, do chord 2 and chord 3 overlap? No, they don't. So the indicator would be equal to 0. So I can have all these indicators. I'm going to say I sub I comma j, where these are our two chords that we're looking at. And we see that's going to be equal to 1 if they overlap and 0 otherwise. So in our case, I sub 1 comma 2 would be equal to 1 because these chords overlap here, and then all of the other ones would be equal to 0. So when we express x, it's just going to be equal to the sum over all of these different indicators, I sub I comma j. And then we're trying to find the expected value of x regardless of independence or dependence linearity of expectation. This is just going to be equal to the sum over the expected value of all of our different indicators, I sub basically I comma j. And we know the drill at this point. The expected value of an indicator is the probability that it's equal to 1, the probability that I comma j is equal to 1, so the probability that two of our chords intersect each other. And we're summing up over all of our possible pairs of chords I and j. So now let's figure out what is the probability that I comma j is equal to 1. So what's the probability that two random chords basically intersect each other? So let's just clear our space here. Now the four endpoints of these chords are all going to be uniformly randomly chosen on this circle. So if I have my first chord here, the two endpoints could be anywhere within this circle, right? So maybe my first endpoint that I draw is here, and then my second one for our first chord is over here, and then maybe for our second chord, the first endpoint might be over here, so I'll call this one 1, and then the second endpoint might be over here. And now when we draw the actual chords on these endpoints, right, they're going to intersect. Why did they intersect? Well, that's just because we had alternating, basically around the circle, we had alternating red and green dots for our endpoints. If the two endpoints of my first chord were like this, well then they wouldn't intersect. And why didn't they intersect? Well, it's because we didn't have the alternating endpoints around the circle. In this case, we had red and then a red and then a green and then a green, right? Versus one more example, if I had this case where I have green, red, now you can see that they're going to intersect because of this alternating pattern. So now when we have four randomly positioned endpoints around a circle, what's the probability that they have this overlapping pattern? Well, we're just placing four random endpoints around a circle. It doesn't matter where exactly these endpoints are. For instance, this one could be here, right? It just matters basically the order. So as soon as we switch to here, they're not going to overlap, but when we go here, they will overlap, right? If I bring this one down here, they're not going to overlap, but when they're up here, they are going to overlap, right? So this just turns into a circular combinatorics question, just like we talked about in QP 50. If I have four randomly positioned points around a circle, right, there's going to be 3 factorial ways to arrange them relative to each other, right, because we have a circle. Again, we talked about this in QP 50, right? If I fix one of my endpoints, I have 3 factorial ways to arrange the remaining 3. So 3 factorial total ways. Now, how many ways are there such that they are alternating, which will give us the intersecting chords? Well, I could either have it like they are arranged right now, where I have green 2 followed by red 1 followed by green 1 followed by red 2 if we're going around this circle counterclockwise, or I could have red 1 up here and then red 2 down here. So I'd have green 2, then red 2, then green 1, then red 1, right? So there are 2 ways that I could have this alternating pattern out of 3 factorial total ways that they could be arranged. So my probability of having an intersecting chord is just going to be 2 divided by 3 factorial. 3 factorial 6, so 2 divided by 3 factorial is just going to be equal to 1/3, most simplified. So the probability that 2 random chords, when I uniformly randomly select these endpoints, the probability that their chords intersect is going to be 1/3 in general, right? So that's the probability that one of our indicators was equal to 1, the probability that I sub I comma j equals 1, and then we just need to sum that up basically over all the possible pairs of chords that we could have. Well, we have n chords, and we just need to choose 2 of them to be in a pair. So this is going to be, we're summing up n choose 2 times 1/3. And now if we wanted to simplify this more, n choose 2, we can write that as just n factorial divided by 2 factorial times n minus 2 factorial, and then that's going to be times 1/3. n factorial divided by n minus 2 factorial, that simplifies down to just n times n minus 1, which we'll have on the top. 2 factorial is just equal to 2. When we multiply that by 3 on the bottom, we just get 6. So our final answer, when we distribute this n inside of here, is just going to be n squared minus n over 6. So that's going to be the final answer. You could write it either way, either n times n minus 1 over 6 or n squared minus n over 6. Same thing, right? Obviously. So if I have 6 chords randomly drawn on this circle, then I plug it in, I get 36 minus 6 divided by 6. That's going to give me 5. So if I have 6 chords, I expect 5 different intersections between those chords, and etc. Right? You could plug in any n value you want into this formula, and this will be our final answer right here. So you can see how linearity, even though this expected value seemed complicated at first, just using linearity of expectation, basic combinatorics, even though we're basically dealing with continuous random variables right here, because they're all uniformly randomly distributed, we just use symmetry to get this probability right here, and then essentially we can work out this formula much simpler than if we were to calculate this straight up. Again, every single time that we do linearity of expectation, it ends up being much simpler than the straight up calculation.